Okay. Can I share my specific area of the screen, or I have to share the entire screen? That's okay, I can do that. Wait a- Okay, everyone, let's start with our presentations. Our project title is Airborne Object Detections and Analysis Using Deep Learning. So I am Dr. Prosenjit Chatterjee from Southern University. With me, Dr. Ang Saman from Wilfred Laureate University, and also one Southampton University student, Sekyu Hira, was also contributed to this research work. So the outline of the project is like we'll begin with the introductions and motivations, followed by the methodology, then discuss the datasets, descriptions, and the model architecture and the experimental results, and which finishes with the conclusions and for the plan for the future. The motivations of this work comes from the rapid increase of airborne object in our airspace. Airplanes, helicopters, drones, UAV, and even bird-like military devices. The manual detections and threat assessments are still standards in many surveillance systems, which leads to inefficiency, slow reaction time, and potential security vulnerabilities. Therefore, there is an urgent need for automated real-time classifications and threat level predictions. Our goal is to build a system that helps defense, surveillance, and civil aviation infrastructures react faster and with a high accuracies. In this figure, you can see that there is a data set has been taken from sample images has been taken um, from the AVD datasets, and which we have some non-threat civilian aircrafts like drones, helicopters, and UAVs, and also we do have some threat level military models. Okay, so but you may notice that it is a very much difficult to distinguish the different and differentiate them, especially when with the low resolutions and long distance image capture. So now there are several applications of this research that we did. It's like and also there is a several applications is possible in this research. It's like defense, like real-time identifications of unmanned aerial vehicles and potential threats, civil air traffic, that classifications and management of aerial objects to avoid collisions and intrusions, smart surveillance systems that integrating AI-based autonomous monitoring, AI research, publicly available benchmark datasets for academic progress. These applications demonstrate why our study is important and it is so timely. So now, the research objective is our planning to build a dual task efficient net before model, which accurately classify airplane, helicopters, drone, and UAV objects, and predicting 3 levels of threats like low, medium, and high. And also, here is our another contribution is to develop a AODTA dataset, airborne object detections and analysis dataset in a new balanced airborne dataset. And additionally, we compared our results with the performance of ResNet 50, which is very much popular convolution neural networks and which is very good in image classifications. Now, our system overview is the pipeline works as follows, like the system takes an input image, passes it through the efficient net before backbone, and the produces two output simultaneously. The aerial object, first one is aerial object class and the threat level predictions, And we use dual cross entropy losses and the Adam optimizer with the learning rate of 0.0001. The scope clarification is like it is important to clarify that this work is not fully focused on object detections. Our focus is entirely on classifications and threat level predictions. The dataset we used actually two datasets. One is AVD and AODTA, which we proposed and implemented here, that is already included cropped and localized airborne objects. However, our model can be integrated with popular detectors like YOLO or faster art CNN for end-to-end real-time system. So to understand the current state of airborne object research, we reviewed relevant literature. Prior works used YOLO, ResNet, VGGs, and other architectures, which are all CNN-based architectures. Some recent works proposed lightweight CNNs or attention-based networks, and other focused solely on drone detections or bird-drone differentiations. However, very few studies combine object classifications with multi-tiered threat level predictions, which highlights the novelty of our research. But also current datasets are often unbalanced, noisy, and incomplete that we noticed. While doing our research, this motivates us to design our AODTA dataset, a balanced multi-source dataset. So now we already discussed that we use two datasets. One is AVD dataset, which consists about 8,458 images with uneven class distributions. That is also a note for everyone and the research community. AODTA dataset that we proposed and implemented here that consists of 26,152 clean balanced images, which is 4 times bigger than the AVD datasets that we developed and implemented in our research, which is built from 4 publicly Creative Commons zeros or CC0 public domain license dataset. We split the AVD dataset into 80/20 ratio, but AODTA datasets into 70/30 ratio with the train and test ratio. Again, you can avail that AODTA dataset with using that QR code. If you can capture it through your camera, and it would give you the immediate link so that you can avail it for your further research and future exploration. I recommend you, everyone, for ISCMI 2025 community, I recommend you to please use this and give us some feedback. Now, the threat annotations. Okay, we do have the leveling of these object types and their threat levels. For example, civilian airplanes, we provide it was given low, fighter jet high, hobby drones low, and military UAV high, and so on. Okay, generally, the birds versus military ornithopter is like very different threat categories. These annotations were carefully reviewed to match realistic threat evaluations by the researchers, and we are also maintaining the similar kind of concept, because the point is like, we try to give the high threat category for military and military-based airborne object, but for any civilians or anything that is benign, we generally give them medium or low category threat level. So now our preprocessing steps include resizing all images to a 32/32/3 matrices. And then after that, we used batch size of 8. And we used data augmentations with rotations, flipping, zoom, and shear normalizations, shuffling. These steps helps the model generalize better, especially since airborne objects vary significantly in orientations, lighting, and scale. In the model architecture, our model uses efficient net before and pretend and on ImageNet, and we add upsampling, convolution layers, 1x1 bottleneck layers, global average pooling, dropout, and batch normalizations. We use 2 separate softmax output heads. In our training setups, for training, we use Adam optimizers, maintain the learning rate of 0.0001, and we used 21 epochs. And we also implemented categorical cross entropy loss for each output. One is threat level and another one is classification level accuracies. As the and use the in the classification level accuracies, we use evaluation matrices for precision, recall, and F1 score. Again, the training was performed using GPU-enabled environments. The results we obtained for every dataset is like 83% object classification accuracies and 80% threat level accuracies. However, due to the dataset imbalance, the model heavily favored high threat samples. Also, we noticed that for high threat, recall is excellent for every dataset. Also, it is low and medium threat recall is extremely poor. Many misclassifications occurs in non-high threat classes, and this highlights the limitations of every dataset itself. Okay, on AODTA dataset, which we proposed and implemented here, that performance significantly improved because of the 96% classification accuracy and 90% threat level accuracies. And the precision recalls are almost going beyond 0.9 or 90% across all 4 classes. This demonstrates the importance of high quality balanced dataset, which is very much required for airborne object detections and analysis research work. Again, for AOD, you can see that the fewer false positives and much cleaner class boundaries and highly stable training curves that AODTA offers a robust data diversity, which helps FECNet-B4 fully expand its capability. We also compared our result with ResNet 50, but when we compared our result with ResNet 50, ResNet 50 only achieves 78% class level accuracy and 70% threat level accuracies. It produces many false positive and false negatives, and it struggled with small airborne objects. So therefore, we found that FECNet is clearly outperforming with the results of or performance of ResNet 50 on both datasets. So now in the performance insight, we observed that UAV and drone shows the high true positive rates, low and medium threat overlap causing confusions. FECNet-B4 compound scaling improves performance. Data balance plays a major role in accuracies, and this reinforces the significance of datasets design. To summarize the key findings, we implemented FECNet-B4 and for dual task classifications that reduces computational cost. Augmentations improves generalizations. FECNet-B4 is significantly more reliable. ResNet 50 is not suitable for the dual task scenario, and AODTA dataset provides the strongest foundations for training. And you can again download that or use that AODTA dataset using that following QR code link. In conclusions, we develop a dual task FECNet-B4 based frameworks. We introduce AODTA datasets, a clean, diverse, balanced datasets. Our model achieved 96% accuracies in object classifications and 90% accuracies in threat predictions. FECNet-B4 clearly outperformed ResNet 50. And this work lays a strong foundation for automated airspace security systems. And thank you everyone for your patience and time. If you have any questions, please let me know. If not, then I have one questions. I got a one questions from one researcher. That is like why, the questions came from this slide, which is like